Дорогі друзі, добрий вечір.
Dear friends, welcome here. Of course, everything most interesting will happen after myself. We will talk to our scientists. The idea of the project dawned on me long before the war. We started to talk about this. We brainstormed this with Timothy Snyder. And of course, this war is very tragic, but only an episode in our great history of the Ukrainian nation. This is an attempt of our enemy to stop us on our great historical path, and this war does not make this project more urgent. This war helps us to understand how urgent and topical this project is. I would like to tell you that Temerty and Sergei Plokhy, we remember how in 2021, half a year before the war broke out, during the Yalta European Strategy, we held a special panel. Well, our professional historians from Yale, Harvard, Neil Ferguson was there. We were talking about the pseudo-historical work of our enemy, a fake of sorts about some brotherhood, And even then we came to the conclusion that this was an attempt to justify some future aggression or war. We felt this. Of course, our enemy is using history or pseudo-history as a weapon. They try to use this faked past as a justification for their interference in our today. And they also want to snatch our future. And of course, their history is the history of hatred. And we expect and we hope that in this project we will tell this story and the history of truth. The history of truth. And maybe even the history of love. Because if you understand better our history, this helps you to love more. And when you love more, then you protect better. And it is important, I think. We have a hope that this project will help to reason what we feel with our hearts, how important for us is this country, Ukraine, and why it is so important. And I'm sure that we have all the chances for this because we have assembled a unique team to perform this unique project. And I'm very glad that from time to time new outstanding scientists join this team. I have an honor to later introduce to you Dr. Olivia Judson, who is an outstanding historian. And she has a very interesting specialization, evolutionary biology. Maybe this word combination will help you to understand how multidisciplinary is this project. 3 or 4, maybe 4 or 5 years ago, before the war, I was talking to Timothy Snyder, and he said, we were talking what the team will look like. And he says, I know one scientist. She is a biologist, but she doesn't even know that she is a historian of genius. And I say, please, Timothy, talk to her until she agrees to take part in this project. And she agreed. So look, when I was thinking inventing this project, I had an idea about how far we can look back into the future, into the past, maybe to the times when people came to the territory of Ukraine or appeared here. And when Temerty told me about Olivia, I understood that with her help, we will be probably able to look into the times when this territory was just emerging and the life in this territory was just emerging. This was our ambition. And Olivia is now publishing her new book about history, both on the planet of Earth, how life appeared on this Earth, and you can understand how powerful she is, and she can understand how powerful is this project.
My great honor, and now I believe great pleasure to welcome you, Olivia Judson. The floor is yours.
It's a great pleasure to be here, and thank you, and thanks to everybody. I want to start with a question. What if this planet had never had life? What if no living beings had ever breathed or swum, burrowed or flown here? How would Earth be different now, a little more than 4.5 billion years into its history? At first, the task seems simple. Remove the life forms. Strip away the trees, the grass, the bushes. Scrape the moss and lichens off the rocks. Vanish the animals. Annihilate the mushrooms. Disappear the microbes. Silence the birds, frogs, cicadas. Empty the oceans of fish, jellyfish, octopus, whales, crabs. Skim the ponds of slicks and scums. And then, with all the life forms gone, you're done, right? Not so fast. Removing the life forms is just the start. To create an Earth that had never had life, you also have to take away the detritus of life, all the things humans have made, of course, but also the fallen leaves, the pearls, the spider's webs. You have to sieve the pollen from the wind and empty the soil of spores and seeds. You have to dig out the guano from caves where bats roost and from islands where seabirds nest. You have to fill in the wallows where sparrows bathe in the dust and repair the pits on the sea floor where whales rootle for food. You have to flatten the molehills, ant nests, termite mounds, and bust the beavers' dams. Once you've dealt with the life of today, you'd have to turn your attention to the past. You'd have to remove the fossils, those prodigious piles of bones and shells that litter the planet, the vast petrified forests, the ancient reefs. You'd have to erase the footprints of dinosaurs, fill in the burrows of long-dead worms, and rub out the imprints of fallen flowers. You'd have to get rid of the amber, siphon off the oil, and shovel away great mountains of coal. And still, you would not be done. You'd have to undo transformations wrought by life that at first appear to have nothing to do with it. You'd have to get rid of all the chalk, much of the marble, some of the diamonds. Many types of minerals, more than half, would have to go too. You'd have to suck the oxygen from the air and take away the ozone layer. You'd have to extinguish the fires, clean away the charcoal, and scrub the soot from the rocks. You'd have to sweep the topsoil from the ground, sharpen the edges of the mountains, and straighten meanders in the rivers. If the planet had remained forever without life, it would have developed along an utterly different trajectory. The sky of that Earth might not be blue. The moon of that Earth might be further away, and the length of the day might not be the same. The climate would be hotter and more arid. The continents might be smaller. That planet would not have as many kinds of rocks. In short, the never-life Earth would not be the Earth of today just without the green. It would be profoundly different, an alien planet, a human or some other animal magicked there, would be killed in an instant, overcome by suffocating air and lethal levels of radiation. It would be a planet not merely lifeless, but deadly. Now, this thought experiment shows that life is a geological force, that it has transformed the Earth, that Earth is not a superficial phenomenon, quote unquote, on the surface of the planet, but rather that the activities of life forms have altered the water, rocks, and air and reached down into the mantle, that hot flowing layer of rock beneath the crust, and high into the sky. In itself, this observation is not new. Almost a century ago, none other than Vladimir Vernadsky, the first president of the Ukrainian Academy of Sciences, among many other accomplishments, published a book called The Biosphere, in which he argued that life is a geological force, writing, for example, that, quote, because the planet has no chemical force that is more constant than life forms taken together, none is more powerful in the long run. But the question that has preoccupied me for the last 15 years is why? After all, at first it seems surprising that life forms could be agents of planetary change. They are so puny compared to Earth, and so fragile and easy to destroy. So how is it that life forms could be so powerful? And as I see it, there are two chief ingredients. The first is time, and the second is energy. And in particular, the ways that life forms have, over time, evolved to use energy. And I want to suggest that the histories of life and Earth can be understood as a series of 5 expansions in the source of energy available to and used by life. With each expansion, the planet became home to a larger numbers of life forms and more different kinds of life, and the impacts of life upon the planet became ever greater. The energy sources are geochemical energy, which is the energy released as chemical reactions carry on between water, rocks, and gases. There is sunlight, there is oxygen, there is flesh, and there is fire. Now, the first 2 sources of energy, the geochemical energy and the sunlight, were present when the planet formed, but the remaining 3 are a consequence of the activities of life. And before I go any further, I would just like to acknowledge the thousands of scientists whose work I have drawn on to be able to make this synthesis. My role has been to pull their work together, not to be in the laboratory peering at microscopes and other equipment. I just want to be clear about that. So here's how I'm going to represent time, this spiral. The present is here at the front. The small tick marks represent intervals of 25 million years. The large tick marks represent periods of 500 million years. And the numbers represent periods of 1 billion years, which is 1,000 million years, going back from the present. And I would like to give you a few points of orientation, because if you're like me, maybe when I began this project, I didn't have a good sense of things. So all of human history occupies essentially the very thin front. That's the extinction of the dinosaurs at 66 million years ago. Plants only appear on the surface of the land 450 million years ago. Animals appear around 550 million years ago. And before this point, there would be no animals, only microbes, and you would enter the vast period of time that geologists call the Precambrian, which, as you can see, is actually most of Earth history. Now, things also become interesting at around 2.4 billion years ago, because prior to this point, there is no oxygen in the air. And when I say no oxygen, I mean no molecular oxygen, O2, which is what we breathe. On the planet would have had oxygen atoms, but those atoms would have been tied up in water and rocks and molecules like carbon dioxide. There was no oxygen in the air. And then I should say that the Earth itself formed 4.567 billion years ago. Well, you might be wondering, what about life? When did life start? And how did it start? And these remain unsolved mysteries. And the reason for that is that Earth is a dynamic planet. It's constantly shifting and changing. Continents move, volcanoes erupt, the sea floor becomes subducted and recycled, mountains become upheaved and erode away. The Earth has erased the evidence. The further you go back in time, the more difficult it becomes to find old rocks. And from about 4 billion years ago, there is almost no physical evidence of the Earth at all. But we run out of rocks before we run out of evidence for life. And so the implication is that life started around 4 billion years ago or earlier. And also, this is an important point, we do know that it appears to have started once, or to put that differently, that all life forms we are aware of today are the descendants of one single origin event. So that single origin seems to have been 4 billion years ago or earlier, but exactly how it happened, we don't really know. We can say something, however, about what they were probably like. And there are 2 bits of evidence that I would like to advance. The first is that for much of Earth history, the only residents of the planet were bacteria, and they were something else called archaea. And bacteria and archaea look the same through a microscope, so for a long time there was just thought to be bacteria. But it turns out that there are 2 fundamental groups of life forms that resemble each other in a microscope, but are biochemically rather different. So they were the first. They appear to have started at the same time, the first species. And we can also say something else, which is that circumstantial evidence suggests that they were what I like to call geovores, earth eaters. In other words, that they were sustained by chemical reactions of water, rocks, and gases, and that they were also built up from those same materials. Now, geovores are real. They exist today. And they were discovered in the late 19th century by another Ukrainian, Sergei Vinogradsky. In 1890, he wrote, "My experiments have established a new truth of general physiological importance. Our planet has life forms that can make a complete synthesis of organic matter without the help of sunlight." And I should say that this was completely unexpected. Nobody had imagined or suspected that such a thing was possible. And to my mind, Vinogradsky's work is some of the most insightful and daring, because he was able to follow the experiments where they led, which was somewhere that nobody had imagined. And so just to repeat, life forms of this kind, geovores, are built from and sustained by the chemical reactions of water, rocks, and gases. And it is almost certainly the case that geovores of some kind were the first life forms, and that they come into two groups, the bacteria and the archaea. Okay, so I'm just going to add, so that's the first energy expansion, is the geochemical energy producing geovores, which sort of starts around 4 billion years ago. Now, at some point after that, the second expansion began, and this was the evolution of bacteria that could photosynthesize. That is, that could make a complete synthesis of organic matter with the help of sunlight. At the surface of the Earth, sunlight is plentiful. So this capability would greatly expand the energy available to life. And judging from traces left in the rocks, this seems to have happened quite early, soon after the appearance of geovores. But we do know, so that's sunlight, we do know that geovores precede the photosynthetic bacteria because all of the biochemistry of photosynthesis, it's first of all a lot more complicated, and second, a lot of it is built on the physiology of geovores of some kinds. But the highlight of this expansion, if it had just remained some bacteria photosynthesizing, you would have seen changes at the surface of the Earth. There would have been colors and large communities of bacteria. But the highlight of the expansion was the evolution of one group in particular, the cyanobacteria, which used to be called blue-green algae. But they're not algae, they are bacteria. And they are very important to Earth history because when they intercept sunlight, they split water molecules apart and they release oxygen. Now, oxygen is reactive stuff. It can form partnerships and compounds of many other elements. And as cyanobacteria began to release the gas, the oxygen began to transform the Earth, creating many new kinds of rocks and hundreds, perhaps thousands of new minerals, as well as great deposits of iron. But eventually, everything that oxygen could have reacted with had been reacted with, and it began to build up in the air. Oops, that's my representation of cyanobacteria. So it began to build up in the air, and this took place, this created something that is known in Earth history as the Great Oxygenation Event. It's the only thing that everybody in Earth history agrees on, is that it happened, and roughly when it happened. But exactly how it happened and why it happened then is unclear. But you can see it in the rocks. It's a line across the history of the planet. And from this point forward, Earth would have oxygen in the air. Not lots, not as much as it does today, but it would have some. And this changes everything, not only for rocks, also for the sky, creates the ozone layer and turns the sky blue. But it also is very important for biology. Oxygen is a rich source of energy. Metabolic processes involving oxygen release more energy than other metabolic processes do, making more energy available for life. So oxygen is the third energy expansion. But as with the sunlight, at first, all you get is more different kinds of bacteria and archaea. So things are, it's still pretty microbial out there. But around 1.8 billion years ago, something very surprising, strange, and unexpected happened, which is that one lineage of bacteria and one lineage of archaea, they fused together to create an entirely new life form called the eukaryote. Now, probably, if you don't study biology, that word means absolutely nothing. But you have definitely seen them. Whenever you look in the mirror, you see one. Everything large, plants, animals, mushrooms, they are all eukaryotes. And they are all the descendants of this unique event in Earth history when one lineage of archaea and one lineage of bacteria fused their lives together. And the evidence, in part, is that the bacterium became a part of the cell called the mitochondria, which is what releases energy when you eat and breathe. All in the cells of all eukaryotes, essentially there are mitochondria. So this gets very exciting, but it's not only large life forms. In fact, at first, it was, again, microbial, but different kinds of microbes. For example, amoebas. So the first eukaryotes were probably very amoeba-like. And this is very interesting because they have new properties, these life forms, the eukaryotes. They are able to have sex. Seems like a good development. And they also have a strong tendency to hunt and eat other life forms, engulfing them and taking in large packets of energy in one go. They would, in other words, eat flesh. But despite this excitement, for the next 1 billion years, which is about a quarter of Earth history, nothing really changed. This is one of the great mysteries in my mind about the history of the Earth. Nothing really changes until, through some course of events that remain mysterious, the first animals appeared. And that happens around 600 million years ago. And that's when the flesh epocha gets off to a really good start. And animals are important, first, because they can be very large. So for the first time, life becomes large. And they also are important because they increase the overall growth of other life forms. They mow. So they're constantly removing, let's say they're removing algae from the surface of a lake. And that makes room for more algae. And so this increases the whole energetic flow through life. And a very easy way to think about this is if you think about the sea. In the sea, which is where the first animals lived, all of the animals are supported by eating single-celled photosynthetic microbes. Everything else, all of the rest of the animals, everything is built up on these tiny, tiny single-celled organisms that are being mown all the time, and then all the other animals eating each other. It's all a consequence of this, and the animals make it all go faster. And so as they began to become more abundant, they also began to transform the earth. They filter water, they burrow, which introduces oxygen into sediments. They build shells and bones, both of which leave substantial traces in the geological record. And they move stuff around, bringing material from the oceans to the land, or from the depths of the ocean to its surface. And as with the appearance of oxygen in the air, the appearance of animals marks a line across the history of the planet that you can see in the rocks. They also provide habitat for other life forms, both in and of themselves, the surfaces, the guts, but also with their physical remains, the corpses, the feces, the old burrows, the abandoned shells. So this introduced a tremendous change to the dynamics of the planet. The final energy expansion is fire. Of all the planets and all the moons in the solar system, Earth is the only one to have fire. That's because to have a fire, you need three things. You need a way to start one, which lightning, for example. You need enough oxygen to support one, and you have to have something to burn. And so it is not until the first plants appear on the surface of the land, around 550 million years ago, that the flames began to flicker. And we know this because charcoal leaves its own fossil record. Fire leaves its own fossil record in the form of charcoal. And ancient deposits of charcoal show that ever since plants first graced the surface of the land, fires have burned. But in order for fire to be a source of energy, well, that had to await the evolution of a fire creature, a primate in the genus Homo that would begin to cook food. Fire is a kind of predigestion. It allows you to extract more energy than you can from the same food eaten raw, especially starchy foods like tubers. Now, when the first primates began cooking is unclear. It's very difficult to pin down the traces of fires, of campfires, and so on, unless they were in caves or in fixed locations. But cooking would remake the physiology of these creatures. It would give them smaller jaws, smaller teeth, shorter guts, larger brains, and it would also liberate them from having to spend hours chewing. This development would turn hominins into humans. And in due course, these fire creatures would domesticate fire, using it to smelt metals, make glass, fire clay, make cement. It was used to enlarge mines. Or think of the steam engine, the internal combustion engine, or the Haber-Bosch process of making fertilizer. These are all technologies of fire. And of course, this would dramatically accelerate the pace of change and the extent and variety of planetary impacts. Well, what does it all mean? And I have to say that personally, thinking about this gives me a profound sense of connection, not only to other life forms, but also to the water, the rocks, the air. And intellectually, I find it very satisfying because I feel that it reveals patterns in the history of the Earth, and it brings humans into Earth history in the deepest ways, and also gives a sense of how humans are different from other life forms. We use a lot more energy. And it also gives us a way to think about what might happen elsewhere. And to that end, I want to finish with a comparison. This is Mars. Oliver Morton, who's a journalist and a planetary thinker, wrote in a book called Mapping Mars, "More than any other planet we have seen, Mars is like the Earth. It's not very like the Earth. Its gravity is weak, its atmosphere thin, its surface sealess, its soil poisonous, its sunlight deadly in its levels of ultraviolet, its climate beyond frigid. It would kill you in an instant." Now, 4 billion years ago, when the first life forms were forming here, Mars was a different world. It's very clear that it had water, possibly oceans. Did it also produce life? Are we, in fact, all Martians really, as some have argued? It's possible that it did. It's possible that there is something still there beneath that dusty, lethal surface. But what I want to suggest is that we don't need to go there to find out that what happened there is profoundly different from what happened here. Thank you very much.
Dobrý večer všem. I'm Timothy Snyder, and I am the chair of the Academic Council of Ukrainian History Global Initiative, and it's my great pleasure to be able to carry on a conversation for the next little while with Dr. Olivia Judson about these arguments. I hope you have a sense, as I do, of the scale and the ambition, and I think the achievement that has been presented to you. I consider myself very fortunate to have been present for this public presentation of an incredibly radical argument about the nature and the origin of our sort of life and our sort of planet. And I'm delighted that this took place here in Kyiv. I'm delighted that it took place within the framework of our project. And just for that, before I begin the conversation, I want to say thank you once again.
Thank you.
So a number of things took place in this lecture, and I'd like to develop a few of them, but I'm first going to restate a couple of them in my own words, just to give you a sense of how I was struck, and I hope you will have been similarly struck. We have in this presentation a very different image of what life on Earth means. In my view, as Victor said, a historical image, because life is no longer Earth is no longer the setting for life, but rather Earth is created or co-created by life. Once one hears that idea, I see you nodding as though you've had this thought before. Congratulations. Once one hears this idea, it seems very intuitive because this is how history in fact works. But the idea that the Earth has been historical almost from the very beginning is radical. There is a new argument here about the character of life, that life has to do with different forms of energy flows that one can chart specifically, precisely, and historically across time. There is implicitly, but I think clearly, a very unfamiliar but persuasive notion of what a human being is, that Homo sapiens isn't just a laterally developed ape among other laterally developed apes, but that our evolution rests on a much longer series of platforms which we can understand, and that our way of living and our way of using energy is specific to us, but much less specific than we would think. And that we have deeply in common many things with organisms that go back billions of years. Or to put it a different way, despite our vanity, that we have no hope of understanding ourselves without the intellectual company, not only of animals and plants and organisms that exist now, but without a sense of how we evolved over the last billions of years. And last but not least, to use a phrase that Americans don't use, but Ukrainians do when they switch over to English, last but not least, it's that kind of reflectiveness that we need. Last but not least, this was also a bit of Ukrainian intellectual history, because I know, having had the pleasure of interacting with Olivia about this work for some years now, that the arguments of Vernadsky and Vinohradsky play a very serious part, I would venture to say a necessary part in the development. So you have been present here in Kyiv in the advancement of some arguments which were made by Ukrainian scientists, very important Ukrainian scientists about whom we should know more. So Olivia, if I could, I'd like to start with a question about scientists. I'd like to start with someone who I know is very important to you, and I think around whose work your work orbits and on whose work you meditate, and whose work I think you have modified in a very significant way, and that is Charles Darwin. So if you forgive the simple way a modest modern historian formulates the question, it seems to me that what Darwin's revolution was to show that life changed over time, interacting with Earth. And that the next step that you have taken has been to show, and of course Darwin had an inkling of this, but the big step that you have taken is to show that life didn't just change over time interacting with Earth, but in that interaction, life was making Earth the entire time. So is it right to think that your argument is a kind of next step in Darwinism and how we think about the relationship in life and Earth?
I think I would probably not put it like that exactly.
But is it correct?
I think what I have So I think that with any subject, there's a very long intellectual development. And not only Vernadsky, who wrote this very complete book, The Biosphere, where he summed up a large number of different directions and also coined the term biogeochemistry. But people before him had also been thinking along these lines. Darwin, as you mentioned, had been thinking about how earthworms transform landscapes. His last book was about earthworms. Lamarck, who is very important in the development of ideas about evolution. Also, he thought that many minerals had been produced by life. So these have a very long fuse, I think. And I think that what I would like to think I could have contributed is a way of thinking about why this is the case. That it's a way of thinking about the nature of life in a different way, and the particular role that energy plays in that, so that it's not that adaptation has the randomness that we often think that it does, but that actually, if you think instead of organisms as representing flows of energy, then you start to see that there are ways in which that is shaping their evolution profoundly. So I would say that I wouldn't say that I'm, but I would say that I'm developing these ideas and providing a mechanism.
I'm here to make the big claims. Let's pause there on the character of your argument about what life is, which is fresh and profound and very striking. To take a step back, we all know that there's a relationship between matter and energy. This is a basic fact of physics. But that versions of the relationship between matter and energy have to do with stages in the history of Earth and versions of the possibility of life is a very striking claim. And I wonder if you can develop this for us further, because in physics, the conversion of matter to energy seems distant and cold and heartless and happens across the universe all of the time. And yet, here on Earth, we're finding versions of this which have a color and shape and form and palpability, which is the thing that we call life. And this is extraordinary, and I'd like for you to develop it.
Well, I think that one of the things that has changed for me as I have worked on this is that my interest in other life forms has expanded tremendously. I think partly because I have come to see each of them as being really instantiations of energy, as expressions of energy, and that they are pursuing their own undertakings, but with this marvelous shape and form. And obviously animals are the most, for me anyway, the most obvious manifestations of that. But even the most microscopic, the smallest, the intricacy with which the flow of energy is being, matter and energy are coming together to make these life forms and send them on their journeys. I have personally come to find it very, very moving. So I've become this sort of absurd person who sort of ushers flies out of the window because I just find them too astonishing.
Yeah, I don't think there's anything strange about that. It does strike me that it's impossible. I mean, it's impossible to listen to the case that you're making without recognizing that it is only our vanity and lack of reflectiveness that separates us from what is on Earth. And yet, I wonder if that vanity and self and lack of reflectiveness has been the kind of thing which has prevented us from seeing your sort of argument. Forgive me for this very simple question about science, but doesn't science often involve people separating themselves and not seeing themselves as changing the environment and seeking an abstract form where they can control for things, whereas the truth that you seem to be telling involves accepting that everything that we have done has always involved an interaction and an alteration. So I don't mean to be too spiritual about this, but is it not the case that the way we have learned to practice science perhaps is the very sort of thing which has prevented us from seeing some of the deeper insights?
Well, I think that these are, science is a social undertaking, and there are currents and changes in science, as in all fields. And one of the things that really strikes me in reading work of 19th century scientists is the incredible breadth of knowledge that so many of them had, and would be writing detailed and thoughtful monographs about whole collections of microscopic organisms, and at the same time being very eminent paleontologists and so on. And I think that one of the things that has been unfortunate in the English-speaking world, at least, is the development of a separation between biology and geology, which was not present for much of the 19th century. And I think that perhaps has been part of the difficulty in thinking about the bridges and the connections, but there are obvious reasons for that also. And I think there's something else as well, which is to do with the way that we often think about the object and the actual experience that the object is having. I don't know if that's going to make any sense, but it's a bit like if you go to a doctor and the doctor, you have your own experience of whatever problem you're having, but the doctor is immediately thinking, I don't have this internal experience, so I'm going to set it aside and consider you as part of a group of people who have this experience. And there's a difference between the third-person assessment and the actual experience that the individual is having. And this, I think, has been one of the tensions in biology. It's not really very fashionable to anthropomorphize. It's considered bad form to sort of imagine yourself as an amoeba. And yet, one of the more surprising papers I read recently was published in the first decade of the 20th century, and it was called The Daily Life of Amoeba Proteus. And it was two people who watched for a week, 24 hours a day, the activities of an amoeba, and they described it. And they published it in the American Journal of Psychology. And I think that this is really interesting because although most of us would not imagine that an amoeba has a daily life, they actually show that if you're patient and you pay attention, you can find out really interesting things about life. And so I would actually say that the bigger problem is not so much scientists being separated from and controlling, but the tendency to forget that organisms are alive.
Or the tendency to forget that their form of life is more similar to ours than it is different. I mean, I think at best, when we consider the social life of two amoeba, at best we might think that someone else is the amoeba. We have trouble recognizing that we too are the amoeba, and that this is the sort of sympathy that we need. I will just make a brief aside. It's touching and important to me when you mention the broad erudition and what we would now call the multidisciplinarity of the scientists of the 19th and early 20th century, whom you read and who you rely upon. It's very striking in Olivia's work that she is doing the kind of thing, again, I'm going to say the thing that you can't say. She is doing the kind of thing that used to be done, which is trying to overcome huge differences in discipline and specialization. This is an accumulation of knowledge and a synthesis of knowledge across many different fields. But the reason it's touching is that we in our project are also trying to do something, in a sense, very old-fashioned. We're bringing together a biologist, paleontologists, archaeologists, linguists, historians, social scientists, in the hope of creating a long-term, total global history of a place. This is the kind of ambition that people used to have in the humanities and in the sciences. And thanks to colleagues and founders and friends, we're able to try to do something like this now. And it's both old and new, because what we're trying to do is to apply not just disciplines, but what technology can tell us. Which leads me to a slightly tragic thought, Olivia, which I want you to maybe make less tragic. As I read your work, but also as I read the work of contemporary paleontologists and archaeologists, I do have the sense that we are closing in on some of the big mysteries, that we really are figuring out some of the basic things about the deep past, which 20 or 30 years ago would have seemed inaccessible. In historical sciences, this has to do with things like, what were the first human cities like? Or where did languages come from? Questions that have been asked for thousands of years, but now, thanks to multidisciplinarity and high technology, we're starting to pin down. In your case, it's the much more ambitious question of what life is and how we understand the history of the Earth. I have this feeling that we're shining these lights within a kind of surrounding darkness, that there's this irony of human life, that we are figuring the things out about ourselves that we need to know at what might be the last moment.
Oh, well, I certainly hope that that's not the case. I think that there's I think that there's a lot of scope for, so certainly I think that there's always more mystery, actually, the first thing. I think I've never seen a scientific question that didn't lead to more mystery. And I think that also humans are unusual not only in using more energy, but being able to be reflective about ourselves. And I mean, it's possible that the amoeba is also a very reflective entity, but we know that we are, and I think that that gives us possibilities also to consider where we are and where we would like to be going. I agree that there are many reasons to be pessimistic, but I don't think that we necessarily that is necessarily too late. I hope not.
Well, it strikes me that it's very hard to see a better future without a clearer view of the deep past. And if one follows your argument about energy transitions, the one that we're in now can go a couple of different ways. We can keep consuming energy at a rate which will change the Earth. And of course, your work puts this thing that we call the Anthropocene in perspective. It's not just the past, 10,000 years in which we've been changing the Earth. We, life, have been changing the Earth from the beginning, but it's coming much faster and harder now. And we have both the ability to do this, but also the ability to recognize it. And I want to dwell on your answer and ask you to go a bit further. There are different ways of processing where we are now. And you hinted at the end of your talk, I think, at one of the misguided ones. There is a notion that now that we've exhausted this planet, we've taken what we can from it, perhaps we should just move on to another one. It seems to me that your work has something quite fundamental to say about that line of thinking.
Well, I certainly think that there will never be a planet as beautiful for humans or as interesting for humans. None of us will ever know any other planet that is more sublime than this one. And I think that recognizing that could potentially lead to an idea about planetary care. I like to think it does. There are ways to use energy that could be made to be positive, to stabilize the planet in interesting ways. I don't see much evidence that that's being actively pursued, but it could be. I think that, this has made me an unabashed earthist. I'm an earthist. I think that, that this is the greatest planet in the universe from our perspective. And I think that it's...
Yeah, let's have a round of applause for Earth.
But I do think that some of these ideas are maybe not spreading as well as they might do.
So it's very, I mean, there's this question about are we alone? And if you imagine the universe is filled with generic planets, which generically could all contain a generic kind of life, then the question, are we alone, seems like a quantitative one. There are countless solar systems, countless planets, so statistically there must be life out there. But if we don't think about quantity and we think about quality, the question poses itself in a different way. Because following your argument, the very specific quality of our planet is that it has arisen, it has grown, it has become what it is in a billions of year long interaction with life, which means that it's not one generic planet among countless generic planets. It means that it is if you'll pardon the expression, historically very specific planet, not one of many. And so the question then might seem to become not, are we alone or are there others out there generically, but isn't it quite miraculous and wonderful and special that this happened here and that we are the thing that happened?
Well, I certainly think so, but I also think that thinking about some of the contingencies, and for me, there are two aspects of Earth history that I'm preoccupied by. One is the fact that this planet was able to accumulate oxygen. If it had not been able to accumulate oxygen, then nothing else would have changed very much. And this planet had the capacity to accumulate oxygen. And then the other is this freakish one-off event of the formation of eukaryotes. And, there are billions of bacteria and archaea. I mean, some populations of bacteria are estimated to be 10 to the power of 27th, which is absolutely mind-bogglingly enormous. There are lots of these creatures around, these organisms around, but they only fused their lives to make a different form of life once. And to me, that is the thing that makes me question what is likely to happen elsewhere.
And of course, in our own much more modest ways, we historians also focus on the things that didn't have to happen. The one-offs, the contingent, the accident in human life, the things that we choose. This event didn't have to happen, our project didn't have to happen, this encounter didn't have to happen, but I am absolutely delighted that it did, and I feel privileged to be part of a project which has brought you here, and I thank you for sharing with us. I thank you, but also Victor thanks you. Yes, Victor. Yeah. Yes, please.
Thank you. Temerty, if I'm right that you want already to say thank you and finish, I have one question or comment, okay? I can't stop you. No, really, because it's incredibly intellectually interesting. It's fascinating to listen conversation between two greatest scientists, but sometimes I have a feeling, maybe wrong feeling, as engineer, because just metallurgical engineer, maybe somebody still in the audience has a question. Please help to understand. There is connection between these beautiful spirals between all these bacteria, etc., etc. And Ukrainian History Global Initiative, there is connection between all this, and I want to give example what kind of questions, for example, I have for myself, and I already tried, to torture. Professor Judson was question. I will give you example. For example, is it possible to think with your approach, with your knowledge, with your finding, there is in the history, what happened? What contributed to the creation of the most unique, most fertile Ukrainian soil? Because this is connection between maybe 100 millions of years, what happened there, and our modern and newest history. Because Ukrainian most fertile soil, this is one of the, let's say, pillar, one of the fundamental fact of our modern contemporary history. Professor Snyder can tell this much more beautiful than I can tell. This is type of questions. This is example. There is potential connections between these fundamental new knowledges and our Ukrainian History Global Initiative. Maybe it's also helpful for somebody. Thank you.
Take that. I can take it if you want.
Well, I'm not prepared yet to discuss soil, but I did have a look at the geological map of Ukraine at some length. And of course, one of the problems with thinking about the way that a lot of it is just marked Precambrian, which is, as we've seen, is actually most of Earth history. So when it's Precambrian, you can't really say very much more specifically. But you do think, to me, what jumps out are these different aspects of the interaction between life and Earth at different times. And for example, these large deposits of iron that Ukraine has date back to before there was oxygen in the air. Or if you think about some of the limestone that used to be on the bottom of the sea, and where the shells of small algae have rained down, and animals were living in the sediment that was forming and made burrows, and those burrows filled up with a different kind of shell, and it hardened and became flint. And that flint from these long disappeared organisms that made their shells out of glass then finds its way into the hands of an individual who wishes to slaughter a mammoth. And I think that there are these connections very obviously to be made with how the planet has been transformed and how that manifests itself in a particular area.
If I may, Victor, I'm delighted that we have this capsule as number one, not just because it's so worthwhile on its own, but because the more I hear about it in connection with our other projects, the more the connections come clear. So Pavlo Shidlovsky, who's here, probably can correct me and amplify me, but if you look at this wall over here, and the human art that was made 20,000 years ago from the tusks of mammoths, these were people who were just getting their hands and minds around the last energy transition, which is fire. Thanks to fire, they were able to cook those mammoths and thereby imbibe much more energy and thereby be at the beginning of this big energy transition that we're still in. Or if you look over my left shoulder, you see a vessel and a female figurine from the Temerty culture, which is from the lands of central and western Ukraine, roughly 6,000 years ago. Again, I'll be corrected by colleagues. The Temerty, and we'll be talking about this in the next session, the Temerty built the largest early cities, the largest cities that we know of in the history of humanity in what's now south-central Ukraine around Uman. And as they did so, and this is disputed among archaeologists, one of the things I've learned in this project is that everything possible is disputed among archaeologists. But one line of argument, thank you for laughing, Professor Muller, that's appreciated. Okay. So in a book edited by Professor Johannes Muller, there is the following sentence. Human activity linked to the Tripolian megasites, that is, these early cities, in particular overexploitation, seems to have been the main trigger towards a severe increase in the amount of grassland steppe formation. Now, if you're Ukrainian, you might think that the steppe, the fertile soil, is just nature, but it may well be that it, like so many other things that appear to be natural, is the result of human activity. And so part of the answer to your question, much of the answer to your question would go back much further, but some of the answer to your question might go back to the prehistorical societies about which we're learning so much more and which will be the subject of the next session.
Thank you very much.
Thank you. Thank you, Olivia.